So first, I would like to thank the organizers to invite me to talk to replace Gottlob. It will be a difficult challenge. And so I will speak about, so my talk will be related to notion of graph convergence. It looks more like a kind of survey talk in some sense, as I will not go into the details of proof. My main aim is to try to make things a bit intuitive, say. So, when one speaks about limits of graphs, the first point is to consider what kind of limit we shall consider, because we have several possibilities, and here are a few. There is a notion of left limit, which has been introduced by Lovasz and al., and which is related to Semeredi regularity lemma. There is a notion of scaling limit, which is quite old and which has been studied in particular by Le Gall. We can also consider some notion of elementary limit, which is related to standard model theory. There is a notion of local limit introduced by Benjamini Schramm for bounded degree graphs. And there's 3 or there's 4 can be put in the same context by the notion of general notion of structural limit, which we introduced with Jarek Nezetril. And more recently, Bollobas and Riordan introduced a notion of local global limits that can be also extended and studied. So, and when one studies limits of graphs, we have 2 main things that we can study. The first one is existence and construction of a limit object. And I will not consider this in this talk. And the second one is, what about the asymptotic structure of the graph in a converging sequence? So we don't look at the limit, but near the limit. And sometimes we can have a kind of qualitative jump between what happens near the limit and the limit object, which represents a limit, the limit. So let's consider some example. So let's go back. What is the notion of left limit introduced by, mainly defined by Lovasz and Szegedi? One possible definition is to consider Lovasz profile, which is the following definition. You count the probability that a random map from a given graph F to Gn is a homomorphism. That is, you simply divide the number of homomorphisms from F to Gn to the number of maps from F to Gn. And we will say that a sequence of graph Gn is left convergent if for every fixed F, this converges. So this is, we have to consider infinitely many numbers, and each of them should converge. And what is known is that convergent sequences can be represented. So the limit of a convergent sequence can be represented by some nice object, which is a graphon. And the graphon is a symmetric measurable function from 0, 1 square to 0, 1. So just to give some intuition of what this graphon means, when you have a graph, you can consider a representation of the adjacency matrix of your graph like some square of 0 and 1. So you subdivide your 0 interval into n parts of same size, and you put some 0 and 1 depending to adjacency. And in the limit, your graphon you can imagine as a kind of graph whose vertex set is the interval 0, 1, and the value w of xy represent the edge density between a neighborhood, a small neighborhood of x, and a small neighborhood of y. So, for instance, if you consider a sequence of complete binary trees, it is these graphs are so sparse that, according to the notion of left convergence, this sequence of binary trees is convergent, but it converges to a zero graphon. Whatever you look in this graph, if you consider some random map from any given f to this binary tree, the only thing that you will see is p independent points. So only the empty graph you will find with probability non-zero. So in this case, the left limit is 0, and it is why, in some sense, the notion of less convergent is considered to be good for dense graphs. You could say that sparse graphs correspond somehow to the kernel of this notion. Okay, so maybe we can try something different. For trees, which have been much studied by Le Gall, we can consider some scaling limit. But here again, if we consider some complete binary tree, well, it grows too fast. And the scaling limit looks like something which is completely degenerated. And it happens that these scaling limits are good when you have graphs that do not expand too much, so that you can have a renormalization which somehow makes sense. So we have assumed that you have some tree, which is some ternary tree like this, which is growing, and the question is, what kind of limit we would like for such an object? For instance, maybe we would like some infinite ternary tree. At first glance, it looks nice, but at the second opinion is that on the left figure, half of my vertices have degree 1, and on my right figure, I don't have even a single vertex of degree 1. So, in some sense, some basic properties of my graphs are completely lost. So another approach could be to consider the easy to state properties about my graph. For instance, any properties that I could express by a sentence in first order logic. For instance, there exists a vertex of degree 1, or something like this. And I would like that my limit somehow would have the same properties as the graph in my sequence. So this corresponds to the notion of elementary limit. A sequence will be elementary convergent if for any sentence in first order logic, this sentence will be either true for almost all graphs, or all graphs but finitely many, or will be false for all graphs but finitely many. And then I could have a limit, which in this case could be this countable tree. It could be of over cardinality, but for instance, it could be this countable tree. But with this countable tree, I am not that happy again, because I have problem with statistics. I would like to somehow be able to choose some random element in my limits, to say what a typical element looks like if I take p random elements. But if I have countably many elements, this is problematic. So in some sense, I would need that my limit, if I want to put a nice probability measure on it, would not be countable. And of course, I could duplicate this uncountably many times, which is somehow what is done in the bounded degree case. I will go back on it. But there will still be some mystery about this, which is that I will have a sequence of connected graphs And in the limit, I will have uncountably many connected components. Why? Because if I choose at random any 2 points, any p vertices, the probability that the distance between 2 of them is at most 1 billion is 0. And this is true for any fixed number. So at the limits, if I choose countably many points, they should be in different connected components with probability 1. Nevertheless, in this case of bounded degree graphs, there is a nice notion of convergence, which is a notion of local convergence, which corresponds to the following. You pick a random vertex in your graph Gn, and you look at the ball of radius r around this vertex. And because you have bounded degree, you have only finitely many possible isomorphism type for this rooted subgraph. And what you ask is that for any radius, the statistics of this rooted subgraphs should converge. And then, again, this is a nice, it gives rise to nice limit objects, which are called graphing. I will not go into the details. Let's say, for instance, that in the previous case, the limits you could see something like this. Somehow that you have a graph which is defined in some standard probability space, and you have the same generic properties as your graph. If you pick randomly vertices and you look somehow what is around your random vertices, what is generated around them, you will find that it is what happens in the limit in your sequence. So this is a nice notion. The main problem here is that it is mainly defined for graph with bounded degree. And I should say that in the title of the talk, I speak about local limit, but for 3 or 4 slides, I will have 2 notions of local limit before I will prove that one is a generalization of the other. So how to extend this notion and possibly and also the notion of left limit to get some stronger notion of convergence which cover all graphs. It is simply by considering some first-order formulas. So, because we consider graphs, first-order formula for us will be of very simple form. So we have the notion of x is adjacent to y. So adjacency is something that we have in our vocabulary. We have conjunction, disjunction, negation, quantification of vertices, and that's all. So this way we can construct formulas. We have 3 variables. And we will say that the sequence will be convergent if the probability that a formula is satisfied converges. So in this setting, we could consider our favorite fragment of first-order logic or full first-order logic. For instance, we can consider, so this bracket here corresponds to the probability, exactly to the probability that a random assignment of the free variable by vertices satisfies the formula. In this talk, we'll be interested by a particular fragment, which is big fragment of first-order logic, which is the fragment of local formulas. A local formula is a formula whose satisfaction only depends on some neighborhood of the free variables. And we'll say that the sequence is local convergent if for every local formula, the sequence of the probabilities that this formula is satisfied in Gn by a random assignment of the free variables converges. And it is a simple remark that when you consider graph with bounded degree, having more than one free variable is not important. Because if you pick at random p vertices in a large graph with bounded degree, then with high probability they will be very far from each other. So somehow the satisfaction of your formula will only depend on what happened individually around each of these free variables. This is why we can somehow reduce the problem to formulas with a single free variable. And when you have a local formula with a single free variable, you can further reduce and simply look at what is the isomorphism type of the R neighborhood of this free variable. And this means that this notion of local convergence extends and coincides with Benjamini Schramm's notions of local convergence for graphs with bounded degree. Okay, and of course, this notion is stronger than left convergence in the sense that what means left convergence, it basically means that you take a quantifier-free formula expressing that you have a homomorphism from F, and this, the probability of satisfaction of this quantifier-free formula converges, and every quantifier-free formula is local. So local convergence implies left convergence.
Yeah. Is there any reason why there is a polynomial but not just a product?
Oh, yes, because somehow if you can consider somehow that there are products that will appear in the picture. For instance, your local formula could be that around x1 you have something, and around x2 you have something, and around x3 you have something. So you have some product. And there can be some interference, and so this can be a bit more complicated, and it leads to a polynomial. So, what about connectivity? As I said in my example with my ternary tree, when you look at the limit of a sequence of ternary tree growing and growing and growing, in the limit you have uncountably many connected components, although all the graphs in your sequence look connected. So at first glance, it seems that connectivity is something that you will lose. But it is not completely true. There is still something that you can save about it. And of course, when you will have a sequence of graphs which will be local convergent, in the limit, at the limit, if we would have some nice limit object. So somehow this is only intuitive point of view because I don't have a nice limit object at this point. But if I add one, what I could find would be countably many connected components which are big, which means with non-zero measure, and possibly uncountably many connected components with zero measures. And the question is, can we say something about the connectivity of the graph near the limit? Somehow, you can imagine that your graph Gn has some parts, like in this hope, that are getting further and further, and somehow it's sparser and sparser between them, and before they disconnect at the limit, you could identify in the graph some parts which are more dense, where it is concentrated, and some parts which are more sparse. So the question is it possible to do so? And to explain how we could do so, I will have to define somehow the typical behavior of three pure kind of sequences. The first notion is the notion of a non-dispersive sequence. What is a non-dispersive sequence? A sequence is non-dispersive if whatever proportion of my vertices I want to find, there is a diameter such that asymptotically, with this diameter, with this radius, I will find a ball that contains this proportion of all the vertices. So almost all the vertices are at bounded distance. So it means that, of course, at bounded distance, I will not find all my graph. So all my vertices, all my graphs in the sequence will not be of bounded diameter or bounded radius, but I want that it is almost the case, that whatever epsilon I give, I can find a radius such that within this radius, I can find 1 minus epsilon proportion of all the vertices. So it will be highly concentrated. And what does it mean? It means that whatever epsilon I can find in the limit, a value d, such that with probability at least 1 minus epsilon, 2 vertices will be at distance at most d. And this means, in some sense, that this could be represented by a connected limit. If I pick 2 random vertices, they will be at finite distance with high probability. So this is the first kind of sequence which somehow is nice, which gives rise to this big component, this giant component. Another notion which somehow mimic what happens with bounded degree graphs is the notion of a residual sequence. A sequence is residual in somehow if at the limit it will break into many pieces. I mean that whatever ball I will consider, whatever ball of radius d I will consider, at the limit, this ball of radius d will contain 0 measure of all my vertices. So this residual sequence has a property that at the limit, all the connected components will have 0 measure. So it means that in the limit, I will have uncountably many connected components to represent my limit. Because altogether, these connected components must have measure 1. So I cannot have countably many. So this is somehow the second typical case which can happen. And a third kind of behavior, which is kind of what happens in my hope, somehow really this part which becomes very sparse, even more sparse than this residual part, is that I have some sets of vertices of part of my graphs which becomes really negligible. And what does it mean, negligible? It would mean that if I take a ball of radius d around my set, not around one vertex, but I take all the points, all the vertices in my graph, which are at distance at most d, from one vertex in my set, then altogether they only represent less than epsilon proportion of all my vertices. So this is really small set. And why do I call them negligible? Because if I take any local formula, which only, so if I have a local formula, it only depends on some neighborhood of my free variables. I say that it is R local if it depends only on the vertices which are at distance at most R from one of the free variables. Then if I have some negligible subset for some parameter d which is sufficiently big, then when I will consider the graph where I remove this set and the graph where I don't remove, somehow I have the same probabilities that a random assignment will satisfy phi. So considering this notion to the limit, we obtain the notion of, I have an example. So for instance, if we have a graph which looks like this, you can see that if I consider this x, the points in this cycle, then if I take some neighborhood, it would break into some pieces which are big, but I removed only the d neighborhood of my cycle is still small. And if I pick any sufficiently local formula, then the probability that it will be satisfied by a random assignment here and here will be very close. So in the limit, I could say that if I pick a subset xn in Gn, in each of the graph, I pick a subset of vertices, I would say that this sequence is negligible if for every distance d, the set becomes d epsilon negligible for epsilon going to 0. It means that if I take this d neighborhood of my set, then the proportion of vertices that I will eventually get goes to 0. So what does it mean to have a negligible sequence of subsets? It simply means that it is something that you can safely remove from your graphs Gn. It doesn't change the limit. Okay, so we have, up to now, we have defined two kinds of sequences and one kind of sequences of subsets. And we shall see that this is exactly the way we can decompose the graph in the sequence. And this is somehow the main theorem that I will take some time to explain it, is that if you have a local convergent sequence of graphs, you can actually mark, you can add some to your countably many marks, and mark by mark S, R, and M1 up to M infinity, the vertices in your graph, such that the sequence of the subsets induced by S is negligible. Somehow it is something that you could remove and you would have the same limit. The sequence in graph by Mi is non-dispersive. So Mi will induce, at the limit, will correspond to something which is connected in some sense. And what is induced by R is residual. So there is one point which is important, is that the sequence of the graph with the marks is local convergent. And here I have to say that it is that it means that you can consider formulas where you use the mark. The marks are in your vocabulary. You can use them in your formula. But of course, in a formula, you can only use finitely many of them, because each of them. You cannot say, for instance, that a vertex is marked. This is not something that you can say. You can say that it is marked by Mi, by M1, M2, or something like this. But you cannot say that it is marked, because you would have to check all the marks. So uncountably many, and you have only a finite formula. Just to, this is something which it is a bit strange how marks work. But so, what does it mean? It means that asymptotically, the structure of your graph looks something like this. You have some part where you concentrate. These are these countably many parts which will eventually have non-zero measure. You will have some residual part, and you will have some negligible sets that will disconnect somehow all of this. And as a corollary, you can see it a bit differently. By removing this negligible set, you find that you can partition your graph into an induced subgraphs, Rn and some subgraph Hin, such that Rn is residual and the Hin forms some local convergent sequence of non-dispersive graphs. And altogether, the proportion of the vertices will, of course, be 1 asymptotically. And the Gn and the disjoint union of this induced subgraph will have the same limit. Okay, so in some sense, it means that when we have this locally convergent sequence of graphs, not only we can figure out where the big components come from, but you can really track them in all the graphs in the sequence. I say all the graphs, it is not completely true, because somehow when I look at some mark, it appears from one stage. It is not present in the beginning in all graphs. Somehow but eventually you'll be able to track any of the non-dispersive, of the big connected components. Only the residual, okay, it's look like this. It's a wall. So let's consider some example to see what it means. Consider this this disjunct union of stars. Somehow stars seems like an easy, a star forest seems like an easy object, and somehow the size of the stars looks nice, but if you look at it, you see that somehow there is one part which is decreasing very fast, and some part which is somehow constant. And this explains why in the limit of the stars, you will have half of the limit will be composed of the measure of the limit will be composed of big components. And this is not difficult to see because if you look at the first star and you consider the probability to be in the first one plus the probability to be in the second one and so on, you make the sum. So you take the limit of the probability to be in the first one plus the limit to be probability to be in the second one and so on. The sum of these limits will converge to 1/2. Right? Take care that somehow you have one, but this is a problem of non-commutativity of limits. Yeah? Limit of infinite sum of limits is not the same as the limit of the infinite sum. So these big components will correspond to this somehow to what you would expect by following simply column by column. But by taking a part of what remains, somehow the smallest ones, and putting them together, you will get small components which will form the residual part, which altogether will correspond to 1/2 of the components. And if you look at this picture, in this picture you find that there is one star which corresponds to 1/4 of all the vertices, one star which corresponds to 1/8, and so on, and infinitely many stars that individually corresponds to 0 measure, but altogether correspond to 1/2 of the vertices. Yeah. And this is an example of a limit object and how you can find this two parts, non-dispersive part and this residual part. So, just to give some hint about, I will not say too much about the full proof, but how we can find the size of these big components. Because it is not, well, it is nice and in some sense not too difficult to find some explicit formula for the size of these big components. And how do? We consider this formula, which is that the distance between x1 and xi, so is at most d in the graph. So distance to x1 to x2, distance to x1 to x3, and so on, up to xk plus 1. All these distances are at most d, and we look at the probability that this formula is satisfied by a random assignment. And if you consider, of course, if we would have these big connected components individually, it is clear what it means. That somehow, if you have something which is connected, somehow you will find that eventually, when d will go to infinity, then you will find what is in the same connected component. But when you consider this in the graph Gn, you have kind of mix. But by taking many free variables, what you will get are actually the moments of the probability that two vertices are close, that two random vertices are close. So what you will get when d will go to infinity, it is you will get the moments of the size of the connected components. And then you can simply consider some inverse theorem to deduce the number of connected components of size lambda. So this is a nice formula. And the fact that when you consider each of these connected components, this part, that each of them will be somehow convergent, follows somehow the same idea that you will consider some multivariate random variable and follow somehow the same way, and use the information that you have in the limit to really construct the marking to identify deterministically in your graph what part you will mark M1, M2, and so on. Okay. I've been a bit fast. So let's see if we can go further. So here we have seen that if we consider some first-order logic, local formulas with first-order logic, we can have some first decomposition of the graphs in the sequences, showing some accumulation part and some residual part. But residual is somehow bounded degree is residual, and we would like to go further. Can we say something more? And this is possible by considering some stronger notion of convergence, which is local global convergence. The notion of local global convergence was first introduced by Bollobas and Riordan by the notion of colored neighborhood metric. And what is the idea? The idea, in the context of bounded degree graphs, was that, okay, instead of considering the sequence of graphs, you consider that you color the vertices of your graph with k colors, as you wish, and you consider for all possible colorings of your graph what are the limits that you can reach. So sometimes for some colorings, you can converge, and then you look at the limit distribution. So what are all the limit distribution of the neighborhoods that you can get by considering some k colorings? And in a more, abstract way, you can say that when you start with some structures, you can lift the structures by adding some new relations, countably many, and you say, okay, I will see all the possibility to lift my structures, to add my new relations, and I will see all the possible convergent sequences for first order that I can get. And I will say that a sequence is convergent if the set of all these limits, somehow, if the set of all these lifts converges with respect to Hausdorff distance. So what is Hausdorff distance? The idea of Hausdorff distance is to consider two sets of points, and you consider for any point here what is the minimum distance of a point here, and for every point here what is the minimum distance of a point here. And you take the maximum of over all the points that you can choose of these numbers. And so if two sets are at small Hausdorff distance, it means that whatever point you choose in one set, you will find a point in the other set which is close. So what does it mean? It means for us that when you have all these distributions of the this probability distribution, whatever distribution we have for Gn, we will find for Gm with big M, we'll find some lift which is close. So we can always construct some converging sequences, or we can always find some lifts which are close in the distance which defined our original notion of convergence. It is a bit tricky. Notice this. But using a standard theorem, we still have some nice property of this kind of convergence that it still defines some compact, it has some compactness property. That every sequence of structure has a local global convergent subsequence. And okay, this can look completely mysterious at this time, so I should give some example. Let's consider a standard problem where we consider elementary, so we will consider elementary convergence on the top, elementary convergence of the lift. So if we consider the metric which corresponds to this elementary convergence, what does it mean? It means that if I take my sequence of graphs, whatever sentence I will take, there is a lift. I can always, for every lift of a graph, I can find a lift of the next one which are close. It means, using Fagin's theorem, and we'll go back to computer science, which is maybe more easy to grab, that if you take any property which is NP, then either all but finitely many Gn will satisfy the property, or all but finitely many will not satisfy the property. So this can be very strong if we take all the possible lifts. If we consider local convergence only with lifts where we only put some unary relation, so it is like a coloring, then we will get some extension of Bollobas Riordan notion of local global convergence. So this is standard local global convergence for bounded degree graphs. And in this setting, for instance, it is known that if we have a sequence with bounded degrees, which is local global convergent, then we still have a nice limit object. I will not go into the detail, but it is still, the graphings are still good. And why did I speak about this local global convergence? It is because they will allow us to get a finer study of the graph in the sequence. If we consider that we have this stronger notion of convergence, then the residual part could be further decomposed, and it is possible to find some expander parts in this residual. And what is the notion? What is the notion which is between this expanding part? We'll say that a subset of vertices will be the epsilon delta expanding if for any subset of vertices which is not too small, not too big, the ball of radius d around this set of vertices expands by at least delta proportion. And so at the limit, this expanding parts will probably break into uncountably many connected components. But as long as we are not at the limit but near the limit, we will get something which will be nicely expanding. It really looks like an expander. And this kind of, the possibility to track this expanding part can be of interest in particular in some algebraic applications. And that's all. Thank you.
Is there any questions?
Are there particular definitions or particular results for planar graphs? Or plane graphs, rather. So it means that you...
Not yet. Okay, so there are some... No, I should say there are some properties for general graphs. So if I take this notion of local convergence, there is a possibility to represent any graph by some probability measure on some space, some nice space, which is a Borel space. And the notion of local convergence will correspond to the convergence of measure, weak convergence of measure. So we know that we can represent, in some sense, the limit by some unique measure from which we can compute all the statistics. On the other side, we expect that for planar graphs, we'll be able to find some nice limit object. But at this time, the best that we could find for this nice limit object are for classes of graphs, so it's for monotone class of graphs, such that the cyclomatic number, so the number, when you consider the number of edges minus the number of vertices, that this number is bounded by a function of the diameter. So this includes, for instance, graph which are with girls goes fast, or a graph with bounded degree, or things like this. But we could not still extend to planar graphs yet. But we hope to be able to do.
More questions? Okay, so if not, let's have another speaker again.